Hi guys, we're going to be talking about kinematics in calculus, so I'm just going to do a little bit of an introduction. So let's get started with our main three concepts. We have displacement, velocity, and acceleration. So you probably already know that with constant velocity you can use this equation, which is x2 minus x1 over t to get whatever velocity you have, and with a constant acceleration you can use v2 minus v1 over t to find your acceleration. But let's say you have some sort of variable velocity or variable acceleration. What do you do then? Well, over here I have graphed a distance versus time graph, and as you can see, it's accelerating at some non-constant rate. So if I wanted to find the instantaneous velocity maybe at this point, right? So the velocity would just be the slope at that point, and the instant velocity would just be the slope of the tangent line, right? And that is actually going to be the derivative of this graph with respect to t at that point. So if I wanted to find v, let's just say this is t equals 2 seconds, right? If I wanted to find v at 2 seconds, I would have to take the derivative with respect to time and then plug in 2 seconds to get the velocity. So similarly, let's pretend this was a velocity versus time graph. So we have a non-constant acceleration in that case. If I wanted to get the instantaneous acceleration at any time, I'd do the same thing, because my acceleration would just be the slope of the tangent line to that graph. Okay, so now we know that if you want to find velocity, you have to take the derivative of position, and if you want to find acceleration, you have to take the second derivative. Okay, but what if we were given some non-constant velocity and we want to know what distance is covered? Well, let's just draw a graph first. This is some non-constant velocity. Well, we know that velocity is the derivative of x, right? So in order to find the distance, we're going to need to do the opposite. We're going to have to take an antiderivative, or an integral. And that makes sense because in honors physics we learned that displacement is just the area under a velocity time graph, and you know that if you take the integral of a certain function with respect to the x-axis, then you're just going to get the area under that graph. So now you know that, let's say you wanted to find the distance traveled between 0 and, let's say this is also 2 seconds, right? You just want the area under this graph, and that would just be the integral of whatever this function is, dv. Similarly, if you pretend this is an acceleration graph, right? You have a non-constant acceleration and you want to find the velocity, you can do the same thing. You can integrate that with respect to the function, and then that would give you whatever velocity you wanted at that point. Okay, now knowing what we just learned about the relationship between displacement, velocity, and acceleration, we can use that information to derive one of our basic kinematic formulas. So this is the equation for the displacement of an object given some constant acceleration. So first, let's start off with, we know acceleration is a constant, right? So in order to get to displacement, acceleration is the second derivative with respect to time, so we need to take a couple of antiderivatives. So we know that a is equal to dv over dt. Okay, so now moving dt to the other side, right? You can take the integral of a dt, and that's equal to integral dv. Right, I'm going to keep them without bounds for now because I don't want to write it all in. But, so, since a is just a constant, you can pull that out, and the integral of normal dt is just going to be t, right? So you end up with at plus c is equal to, and this just becomes v plus, I don't know, b, right? So now we just get v is equal to at plus and then let's call this a new constant because it's technically c minus b, but it doesn't matter. It's just a random constant, right? D. So now let's try to figure out what this random constant is. And you can sort of use limiting cases. So at, let's say, t equals 0, when acceleration has no effect on it, then v would just be equal to d. So now it makes sense if d is what we call our initial velocity, or v naught, right? So this is just v naught. So this gives us v as a function of t is equal to at plus v naught. Okay, this is we're getting there. So now what we have to do is we have to repeat these steps again. We have to take another antiderivative in order to get to displacement, because we know that velocity can be written as dx dt, right? So now, doing the same thing, moving the dt over to the upper side, we can get integral at plus v naught dt is equal to the integral of just dx. So now, if you integrate both sides, the integral of whatever constant times t is just going to be 1/2 at squared. This is a constant, you can sort of pull that out and just multiply by t. Plus c is equal to x. Right, but since we're looking at displacement, right, we're only looking at change. You don't really need the c because we don't care about the initial value of the problem. So now you can just rewrite it as delta x is equal to 1/2 at squared plus v naught t. And that's how you derive one of our most important equations in kinematics.
From chapter 4 in Halliday. And it is the acceleration of a particle moving only on a horizontal xy plane is given by a equals 3ti plus 4tj, where the vector a is in meters per second squared and t is in seconds. At t equals 0, the position vector is r equals 20i plus 40j, at which locates the particle, which then has the velocity vector v equals 5i plus 2j. At t equals 4 seconds, what are a, its position vector in unit vector notation, and b, the angle between its direction of travel and the positive direction of the x-axis. So first off, going into a, we have the equation a equals 3ti plus 4tj. And so in order to find the position vector, we have to use the acceleration vector and integrate it twice, since acceleration is the second derivative of position. So first, let's find velocity. And so you can take the integral of the acceleration vector, and you can just treat I and j as constants. And you get that the velocity is equal to 3t squared over 2i plus 2t squared j plus some constant. And this constant is going to be the velocity vector at t equals 0. And so you end with a final result of the velocity as a function of time is equal to 3t squared over 2 plus 5 I plus 2t squared plus 2j. And now finding the position. Position is once again the integral of time. And so
Okay, so now we're going to go over 2010 question 3, and here's the question. So for part A, we know that velocity is the integral of acceleration, so it's asking for the expression of the velocity of the skier as a function of time during the acceleration. So that's up until terminal velocity, so we can plug in our given equation for the acceleration up until terminal the terminal time t, which is a max sine pi t over big T, after taking out some constants and integrating, then this is what we get. And after plugging in the limits, we get negative a max big T over pi, quantity cosine pi, variable t over big T minus 1. That's from 0 to big T. Okay, so for part B, we're asked to find the work done by the net force on the skier from rest until terminal speed is reached. And we know that the work done by the net force is equal to the change in kinetic energy, so that's indicated in this equation over here. We know that it's from rest, so V initial will be 0, and then for V final, we're just going to plug in the terminal time t as the variable t into our previous equation that we derived over here. And so then after doing the math, then we get 2ma squared big T squared over pi squared is equal to the work. For the third question, we're asked to determine the magnitude of the force exerted by the rope on the skier at terminal speed. So we know at terminal speed no longer accelerates, so then the net force will be equal to 0, and this is our net force equation, so then we know that the force from the rope is equal to mg sine theta, which is the component of gravity in that direction. For the next question, we have to find the impulse imparted to the skier, and as soon as we see total impulse, we know that we have to take the integral of f dt, and because we know that f equals ma, and this is during acceleration, then we can plug in a equals a max sine pi t over big T for our acceleration, and then we can pull out m and a max as constants, and then after we integrate, we end up getting 2 ma max big T over pi.